So welcome to DVCon 2021. So in this presentation, we're going to talk about spiral refinement methodology for silicon bug hunting using formal verification. My name is Peng. I will be giving the presentation, but my coworker Mark and Jin has done a lot of work in this area. To be successful with formal verification, the user has to wrestle with a lot of success factors. So we want to formulate these success factors into radar charts. So in the diagrams on the right-hand side, you can see the 6 success factors we have captured in this radar chart. So for example, the complexity of the design, the control of the formal engines, the quality of instructions, the completeness of constraints, the proximity of the initial state, and the accessibility of formal experts. So this radar chart can help guide the deployments of formal verification. It can also help the project team to refine each of the success factors incrementally. As some of the bugs can be very deep inside design, so multiple methodologies have been proposed in DVCon before to hunt those bugs deep in the design. So one of the approach is called goal posting. So by leveraging fire or cover targets inside design, we can use those targets as sub-goals and to launch subsequent formal runs. So by leveraging some of the sub-goal that has been exercised by formal, we can build on top of each other and then subsequently reach the final target or bugs. Another approach is called river fishing. So as simulation has been exercising design, some of the simulation stimulus may be exercising the design very close to the bug or targets. So by leveraging those simulation stimulus, we can launch formal verification from those as interesting starting point, and then formal verification can hit those target or bugs subsequently easily. Using formal verification for bug hunting can be slightly different from the traditional usage of formal verifications. So for example, we do not want formal verification to handle the whole design. It can be very, very big. So we want to over abstract the design. So we want to abstract the design so that formal verification can focusing on the modules or part of the design that has the bugs. Now we can also over constraints. Now, since we already know the configuration and the mode of operations, so we can constrain the design, constrain the interfaces, so that formal verification will focusing on that particular operation of the design. Now, at the same time, as we have observed the bug scenario in the lab, we want to capture those bug scenario using assertions. At the same time, it's also very important to capture the preconditions and the configurations and other scenarios that lead up to the bugs. Now the bug could be very, very deep inside design. So as we already have this original initialization sequence, so we do not want to run formal verification from time 0. So we can leverage the simulation initialization sequence to initialize the design so that formal verification can be launched deep inside the design. Formal bug hunting is a refinement process. So initially, we are on the outside, very, very far away from the bug. So we want to classify the process into 3 different phases. In phase 1, in the initial phase, we want to gather all the information. We want to set up the formal environment to make sure that we have all the successful factors in place to start the process. Now, in the second phase, we want to start optimizing each of the success factors so that we can define the scenario close to the bugs. So as we illustrate later on, you can see that this could be an iterative process. So phase 3, the final phase, we want to optimize each of the success factors so that we can ultimately find the bugs. So for the rest of the presentation, we're going to share some of our experience using this spiral refinement methodology on 3 examples. The first one is a DDR3 controller. The bug was found very late in the design cycle after the design has already been fabbed in silicons. In the second case is a memory controller. The bug was found in the lab while the design team is trying to bring up the silicons. Now the bug happens like 2 to 3 hours after the design has been running 2 to 3 hours in the lab. The final one is the packet scheduler. Some of our design team has been using this methodology for a while. So after they have gained some experience, they have also applied this methodology for formal closure. So we want to share some of the experience as well. Now for the DDR3 controller, the bug happens when there's a sequence of write command to a specific memory bank. When that happens, the DDR3 protocol will be violated. To set up the design for formal verification, we follow the spiral refinement methodology. We capture the 6 success factors here. Now, for the complexity of the design, we picked it up at the right level of hierarchy. The goal is to reduce the complexity of the design for formal location as much as possible. Now, for formal experts, unfortunately, this design team do not have any formal expert in-house, and that's why they're working with the two vendors to set up the pilot project and at the same time to gain some formal knowledge as well. Now, for formal engine, we want to make sure that the formal engine has sufficient control of the design, so that's why we black box the memories and also some of the unessential part of the design. For quality of assertions were written to capture the bug scenario and the sequence of events leading up to the bugs. So by using those assertions as sub-goal, we were able to deploy formal goal posting to recreate the sequence of events in formal. Now for initial state, this original simulation has a very good initialization sequence. So by combining the simulation initialization sequence and the sub-goal, we were able to launch formal applications very close to the bug scenario. Now for constraints, so the design has 5 AXI interfaces. So initially, we disable 4 of the interfaces to focus formal application on one interface to exercise all type of transactions. So once we found the bug, we enable the other 5 interfaces so that we can study the interactions between those interfaces. So in this case, the SoC design failed in the lab during post-silicon testing. It was bad, but after some testing, the memory controller was identified as the source of the problems. Now, in this case, they are fortunate to have formal experts in the team, so they were involved earlier on in the formal verification process. As you can see, by having formal experts in-house, they can quickly optimize the success factors. And for formal engine, memory and also an essential part of the design were turned into black box to make sure that formal has adequate control of the design. Now, since we are in phase 1 of the methodology, we want to collect all the essential information and understanding to create the formal environments to find the bug. Now, for assertions were written to capture the failure scenario. And since we don't know what caused the bug, a lot of cover property were written to monitor the combination of events that lead to the bug. Now, simulation were able to exercise some of them, but simulation was not able to exercise the bug. Now, for initial state, the original mean time before failure in silicon was at least 2 hours. That was very long. By studying the sequence, we were able to understand the setup, the configuration of the design, so that an essential sequence can be created to set up the design for formal verifications. Now, for constraints, since we are in phase 1, we intentionally leave all the interface unconstrained so that formal can explore all the possible scenarios that lead to the bug. So for phase 2, we want to continue to refine the success factor so that we can set up the formal environment sufficient to hit the bug. So for the complexity of the design, we want to home in on the functionality of the memory controller by eliminating some of the subblocks. And then for the formal engines, we want to give the formal engine extra flexibilities by adding cut points to some of the configuration registers, counters, and final state machines. As it turned out, the quality of assertion is the most important factor of this bug hunt. So initially, formal verification was able to hit like 85% of the prerequisite conditions. So after some refinement, formal verification were able to hit the bug in less than 10 well-timed transactions. Now, however, the sequence of events is not exactly match what we have observed in silicons. So that leads us to question whether there are multiple causes of the bug. Now, for initial states, as the project team continued to debug the scenarios in the lab, we were able to refine the initial state to be closer to the bug scenario. Now, initially, formal verification found the bug without any constraints in a completely unconstrained environment. So now we are adding interface constraint and also configurations constraint so that we can refine the context example to be as close to the real scenario as possible. So in phase 3, we want to understand the cause of the bug, the effect, and the potential fixes. Now, to explore the different scenarios of the bugs, we want to add a few subblocks back into the formal run. So although this will increase the complexity of the formal, but we are not particularly concerned because we already have a very good handles on the other success factors, especially the controlling the formal engines. Now, by using the caching mechanism, formal knowledge for 72% of the assertions have already been cached. So by leveraging the formal engine that has been performing well, we can improve the formal run significantly. Now for phase 3, we want to understand all the causes of the bug. Now in this case, we still want to find the scenario that has observed in silicons. So to do so, we refine the assertion and the preconditions to find the exact combination and sequence of events that lead to the silicon bugs. Now this turned out to be a very good exercise. It helps us understand the shortcoming of the design. At the same time, it ensures that we have fixed the bug correctly. Now for initial state, after we have run formal with a number of initial state, we were able to identify a number of configurations that will enable the bug. At the same time, a few other configurations that will disable the bug scenario. So using this information, we were able to identify the software fix for the bug. So after the software fix, formal verification will apply again to make sure that the software fix was sufficient to prevent the bug from happening in the first place. So this spiral refinement methodology was originally developed for silicon bug hunting. So after some of our users has been using this for a while, they feel very comfortable with it and has been adopting it for formal verification closure. Now in the formal verification closure flow, the methodology is very similar. So in phase 1, we are focusing on abstracting the design. We want to make sure that formal verification can reach deep inside the design. Now for phase 2, we are focusing on proof and the bug, exploring the bugs found by formal verifications. And for phase 3, we are focusing on formal coverage. In this case, we want to use this methodology for formal closure on a package schedulers. Now, as we are in phase 1, we want to collect all the information. We want to set up the design for formal verifications. Now, as a packet scheduler could be a very complex design and could have very long latency. So in this phase, we want to focusing on reducing the complexity of the design. So we want to reduce the number and size of the channels so that formal can focusing on a few channels. And also the original design, the packet size could be very long. We want to set up a design so that we can use short, small packets. And also in the original setup, there's the design allows a large amount of bufferings for outstanding transactions. We also want to optimize this into a small buffering scheme. Now for this particular design, we have access of the formal expert, so we can quickly improve this formal success factor. And therefore, the formal engines, we want to optimize the memories and also turn the unessential part of the design into black boxes. Now for assertions, since we do not know where the bugs are in this design, assertions are written to monitor the critical parts of the design. So two of the areas we pay special attention to are the data integrity and also the credit-based scheme. So assertions are written to make sure that the data has transferred through the scheduler correctly, and at the same time, the credit-based scheduling schemes is working correctly. Now, secondly, for the initial state, we have a known good initialization sequence for this particular design. As you can see, we are keeping the same initialization sequence throughout the whole formal verification process. Now, for constraints, for this particular design, it consists of the transfer protocol. It consists of a multiple AXI bus interface, and it also has configuration and memory interfaces. So all those interfaces has been constrained correctly, and they were kept constant throughout the whole formal verification process. So for phase 2, we want to optimize each of the success factors so that we can be successful with formal verifications. Now for complexity of the design, we want to reduce the design complexity further by customizing the design abstractions. So for example, if we are focusing on the data integrity, we want to focusing on the data part of the design and then optimize the rest. On the other hand, if we want to focusing on the credit-based scheduling scheme, then we want to focusing on the control part of the design and optimize the rest of the design as much as possible. Now for formal experts, so we are leveraging the formal expert we have in-house and the tool vendor to set up the design so that we can perform multiple runs on the multi-core server farm environments. Now for the formal engines, we are running formal verification using all the formal engines to look for proof and violations. At the same time, we are caching the formal informations. Now we try to be as efficient as possible by leveraging the 4 levels of multiprocessing. Now for assertions, we want to improve the assertions based on the feedback from the tool. So when the formal is running, it shows the engine health dynamically and also the active logics being analyzed by the formal engines. So we monitor those data, and based on those information, we fine-tune the assertion, and also in some cases, we add additional assertions. We also add data independency and non-determinisms into the assertion so that formal can have better control of the design. Now for initial state and constraints, as we mentioned before, we're keeping them constant. Now for this particular design, there are 4 levels of multiprocessing. So talking to the design team, there are 14 commonly used configurations for this design. So we can set up formal run to focusing on these 14 configurations. Now at the design level, we can set up formal run with different abstractions. So for instance, we can set up formal run to focusing on the bypass mode, or we can use formal to focusing on a single channel or stream of the design. We can also reduce the buffering threshold so that we can trigger the discard mechanism early so that we can verify the mechanism is working correctly. We can also constrain the input to just test a particular channel or functionality of design. And as usual, we can always black box some of the modules or instances inside the design. At the session level, we can leverage the mechanism in the tool to set up multiple sessions with different combinations of targets and constraints. At the engine level, the tool is doing a very good job already. So the tool can launch formal runs with a full set or partial set of engines in the multi-core environments. And at the same time, it will aggregate all the results back into a single database. The diagram on the right-hand side is showing the progress of formal verification over time. So for particular sessions, the y-axis is showing the number of formal properties, and the x-axis is showing time. So as you can see, the number of proven properties showing in green over here is increased over time. It means that formal verification is making progress and proving more and more properties along the way. Now the diagram on the bottom is showing the engine health. So we can see that engine number 12 is making good progress on the design, while engine number 17 is having problems verifying this particular property. So for phase 3, we are focusing on formal coverage. We are trying to keep the formal environment as constant as possible. As you can see, the purple boundary is more or less the same as the green boundary. So for constraint, we are keeping it constant. For initial state, we are keeping it constant. Formal expert, it is the same team. Now for the complexity of the design, we are not doing more abstractions anymore. Now, however, for formal engine, we are now changing the orchestration of the formal engine to focusing on formal coverage. Now for assertion, we measure the formal coverage in multiple ways so that we can get a complete picture of the formal coverage structurally and dynamically during the formal run. So for formal coverage, we measure formal coverage in multiple ways. First of all is the functional coverage. These are focusing on the properties inside the design, the assertion statement, cover statement, and cover bin statements. We want to make sure that formal verification was able to exercise those assertions sufficiently. And this is especially important for bug hunting because we want to make sure that formal verification were able to hit the conditions leading up to the bug and finally the bug itself. Now for structural formal coverage, this is computed from the structural cone of inference of the property. So this is very useful at the earlier on in the design cycle. By using the structural formal coverage, the user can determine whether there are holes in the design where more assertion need to be written. Now finally, the proof cone formal coverage. The proof cone formal coverage report the structures analyzed by all the formal engines, which is normally a subset of the structural cone of inference. It provides an engine level view of the formal coverage. So this is very useful at a late stage. It allows the user to determine whether sufficient formal verification has been done. On the diagram in the right, you can see the hierarchy of the design and at the same time the total formal coverage. Now, the total formal coverage can be from one formal run or it can be aggregated from multiple formal runs. So just like simulation, we are measuring coverage from statement, from branches, from toggles, from balancing machines, and state transitions. As you can see, we are doing very well on statement and branch coverage. The coverage is very good on some part of design, but not so good on the other part. To summarize, we have presented the spiral refinement methodology. We know that finding silicon bug is a very challenging process. So the spiral refinement methodology and the rated chart help highlight the success factors for formalifications. So they help guide the user of the process and allow the project team to optimize each of the success factors incrementally. So we talk about two examples, the DDR3 controller example and the memory controller examples. So in the memory controller example, for phase 1, we set up the design for formalization. For phase 2, we're optimizing each of the success factor and find the bugs. In phase 3, we are understanding all the potential cause of the bugs and also verify the fixes. So this methodology has also been adopted for formal coverage closure. We talk about the package scheduler. Now for phase 1, we set up the design for formal verification. For phase 2, we are targeting functional coverage and structural coverage. For phase 3, we perform formal coverage closure by using the proof cone formal coverage. Now finally, this process is not just technical. When some company adopt this methodology, they have to make some organization changes as well. Thank you very much.